Okay, so this we're going to start looking at performance assessment in architecture. Performance. My spellings are very bad. Performance, right? So performance assessment, performance issues. But basically, uh, and this question usually comes as its own thing in the exam or as in part of another question in the exam. So it's actually very important to know how to make these calculations. So what this goes about is basically just how we can assess the performance of a computer based of course on how fast the clock speed is and the number of instructions we're executing and the number of cores. So if you've read up on your theory, you should already know what most of that jargon is. And I'm assuming we won't all get lost when I start explaining most of this stuff. But firstly, we're going to look at a few very important formulas which will actually help us when it comes to solving these questions. The first and the most simple one that we know of should be the period being equal to 1 over the frequency, right? And vice versa. This one should be very simple. So that one being equal to period, right? Period, which is seconds, of course, seconds for something to happen, and then we have frequency there in hertz. So sometimes you might be given your question in gigahertz, megahertz, etc., etc. So we'll actually need to convert these to normal hertz. We have to convert these to hertz units when doing our calculations, right? Then we have CPI. Now CPI, personally, I like calling it average CPI like that, or CPI average, because this is what this is. Because each instruction when we're dealing with these things, so basically, each instruction in your computer has a certain number of instructions, a certain number of cycles it needs per instruction. That's why it's called CPI, cycles per instruction, right? So each instruction, so you might have, let's say, a load, you have a store, you have an add, right? So each of these might require a certain number of CPU cycles to execute. Say this one requires 1, this one requires 3, this one requires 2. So you might have this stuff over here. So that's what CPI for each of these instructions is. And then when I'm doing this calculation, we're going to be finding the average of that CPI. Hence why I personally like to call it CPI average. But yeah, you can just say CPI. So like in the recommended book you guys are using, it should just be called CPI. Now this is equal to summations back in discrete mathematics. Summations up to n is equal to 1. So if you've been doing your discrete mathematics, this should not be very hard, so I will not elaborate on this further. That's a joke, by the way. But what we're going to do is, this might look complicated, and actually remembering this, personally, I went through the entire year and actually never really memorized this entire thing. As in, now I can understand it, but basically what they are saying is, for each of our instructions, right, we're just going to say our instruction, let's say CPII, right? Then we're going to say that times our instruction count times our instruction, so the number of instructions. So we might, let's say, have our program might have, let's say, 1000 instructions. Remember, we have our load there, we have our store, and then we have our add there, right? You might find that maybe our load only has like 500 of those instructions, our store is only like 300, and then our add occupies the remaining 200, right? Something like that. So we might have a certain distribution like this, right? And then of course we have their CPIs 1, 2, and then 3 there. So now what we're getting is, we're getting the instruction count for this one. So this is our instruction I, and then this is our instruction count for the entire program. So we're getting the instruction count for that specific instruction times its CPI over the instruction count for the entire thing, right? Then we're adding them. So we're going to say, okay, see, so this is, let's say, 0, right? So 0. Now I'm going to say, okay, CPI 1 times I there, so I'm going to say 1 over instruction count plus our CPI there, all the way up to n. So basically this is all this means here, just to break it down a bit. But basically just get it, for each of our instructions we're getting that instruction CPI times the instruction count, the fraction, the number of instructions, like how many times does that instruction appear in our entire code over all the instructions in our code, and then we're just repeating that for every instruction that we have. So this is basically what we have there, what all that means. Then now, the most important formula is time. So this is time taken to execute a certain number of instructions. So this 1000 instructions that we have here, how much time will it take for us to execute that? Well, we say our instruction count for the entire thing times our average CPI, again I just personally like putting AVJ there just so I don't confuse myself, times our period. Remember, period is in seconds, right? So period, this is in seconds. So by finding this, we can actually calculate the amount of time it takes us to execute a certain number of instructions in our machine, right? So these are just the first few formulas that we have, and then you have something called MIPS, or millions of instructions per second. So usually you're asked to say calculate the MIPS rate, etc., etc. So the way we calculate this is basically just by saying our instruction count is equal to our period times 10 to the power 6. Or if you do not have that, you can just say the frequency over CPI times 10 to the power 6. And if you have time or your own free space, you can actually just move from here to there using all those formulas. In fact, this is not period, this is time taken, not period. But yeah, you can actually move from either one of these formulas to go to the next thing. Yeah, that's... Wait, is it time taken? Anyway, I might be confusing myself. But you can always move from any one of these formulas to go to the next one, right? And then finally, this is an important one. We have something called Amdahl's law. I really butcher these names, but it's called Amdahl's law. I think that's a spelling. My spellings are very bad. I don't even know how I've managed to get to university, but anyway, we have Amdahl's law. Now, what Amdahl's law is, there's a lot to read up on this, but just to put it extremely brief, we know that let's say we have our instructions, right? We have those 1000 instructions. Now, computers, you've talked about multiple processors or multiple cores on the computer, right? Talk about multiple cores on the processor, etc., etc. So what is all this? Well, basically what Amdahl's law states is that, okay, if we have all these cores, right, then we have all our code. So let's say we have 10 cores. Now, not all of our code will run concurrently, while we're saying one instruction after the other. Some of that code can be what we call parallelized, where you can run we can run the same instruction on multiple separate cores. You get, right? Hence speeding up the process. Because imagine, for instance, just in reality, there's an amount of work you can get done alone, but then if you do it in a group, that will be faster, isn't it? But then there's certain work that not a lot of people can do at once, that you just have to do on your own. But then there's other work where you can do it in a group. The same thing. So imagine you've been given a mixture of that work, certain work that you have to do on your own, then certain work that you can do in a group. So now basically that's what happened. So you have what you call F. F is the part that can be run on multiple processors, right? Or that's parallelizable. Basically, it can be run on multiple processors at the same time. And then you have 1 minus F. So since F is a fraction of the instructions that can be run on multiple processors, this is concurrent code, right? Once it has to finish for the next one to go on, etc., it cannot be split onto the multiple cores. So basically, if you have more concurrent code than you have parallelizable code, what means is that you can have 1,000 processors, 1,000 cores, right? You can have 1,000 cores, but you won't get that huge of a performance increase, as opposed to if your entire code was parallelizable, meaning can be run on all those CPUs. What will that mean for your code? Well, the more CPUs you the more cores you add to your CPU, the faster your program will run, hence reducing the amount of time. Now, we've talked about all of this. What do we use it? Well, we have a simple ratio. We have a simple formula that we use, which is called speed up, right? The speed up of the code, speed up is equal to 1 over, then we're going to say 1 minus F, the part of our code that is not parallelizable, plus F over N, like that. So this is just a single way this is just one formula that we're going to be using a lot. As I start doing my calculations, but what this basically means is our speed up. So this is more like a ratio, right? So imagine 1 is our original speed, and then we're going to find the ratio based on what is our new speed after we add n. So n here being the number of cores that we've added, because remember this f over here, this one is affected by number of cores. So the more we have here, the less this entire thing will become. Hence, of course, we'll get a larger speed up. So these are just a few formulas we're going to be using for performance issues or performance assessment.